G'day YouTube, JB from Oz again. This is a quick set of 18 tips that may help you when you're either selecting or attempting to build a 3D printer kit. This is based on a friend's 3D printer that I'm rebuilding for him after he was having lots of issues that he just couldn't seem to get right.
Okay, so the reason for the rebuild is that my friend built this from a kit that I supplied him. And he was having some difficulty, and he managed to find some fairly unique ways of fixing the problems he was facing, which involved, shall we say, some rather interesting methods. He asked me if I could print another set of parts for him because in the process of making things fit and not quite sure what and why, he caused a little bit of damage to some of these parts. So I said, look mate, no worries, bring it to me, I'll have a look, I'll pull it to bits, I'll fix it up, I'll replace the bits. And as I was going through it more and more, each time I looked at what I had to do to replace it, I was thinking, well, yeah, look, that's not going to work, and this is a bit naffed, and maybe what I should do is do a video on how to actually build a printer so that other people can follow along and build one that they're quite happy with. So here we go. In doing this video, I'm wanting to show you some of the common mistakes people make and how to resolve them. Problem one, in no particular order. This is the heat bed, and typically it'll be soldered onto some wiring. We have a thermistor here which is used to sense the temperature of the heat bed and provide feedback. But there's no strain relief. So what will happen with this, as the printer moves backwards and forwards, point of strain is going to be right where the solder joint ends and the copper begins, and typically what will happen is you'll end up with a failure. One of those leads will come off and your hot bed no longer works. Sometimes it's useful to add a little bit of heat to make things fit, and typically you'll find that around some of the nut openings. Depending on the quality of the kit that you get, you may also have to do a little bit of extra finessing to make things fit. This kind of level of heat is a bit over the top. The other thing to consider is that when you're working with plastic in this sort of kit, we all know that you're the strongest person in the schoolyard, but the kit is not the place to demonstrate that. Why that is, you know, you've got 10mm metric threads, a couple of really solid nuts. You can tighten these plastics up so far that they just split, and I don't know if you can see there, but that's a split through that's been caused by over tightening that connection. So just go easy on it. In the kit that I supplied my mate, I included a whole pile of crimped connections and additional coverages so that you can take things like the power supply and make them safe. I tend to like clip together assemblies that don't use additional fasteners, because when you're building one of these things, you like to know that you're doing the best job you can for the lowest price you can. We're not actually manufacturing a whole pile of these things, but if you were, every time you save a little bit of money on something, you know that it's going to pay off in the long term. When you're doing wiring for connections, and especially these high current connections, you'll notice here these are crimps, not solder joints. One of the failures that people often get is soldering bits of wire and then putting screw terminals on there. 3D printer, there's lots of vibration. Those are points of failure because the solder will work harden. When it work hardens from the vibration, you'll find that a small gap appears, resistance builds, heat heats up, your solder starts to move, you get more resistance, and then eventually you get a runaway failure of that joint. I've had that happen to me previously on a joint on the board where the through-hole solder on the connection pin here was just not good enough, and so the resistance failure happened here. Luckily I was able to save that board and keep going. When you're in the market for a 3D printer, there's a whole pile of options that are available these days, and a lot of the choices out there include some custom boards or totally proprietary designs. I've got a favourite just with the Arduinos because they are fairly easy to work with. You know exactly what you've got, open source software, everything, you know you can fix it up. The hot end. Now this is one of the things that China has come along really quickly with a lot of options. Now for some reason, let me see if I can see this. There's options in the hot ends to do with the heat resistor that actually generates the heat, plus also the actual hot end itself. This one looks like it's using a resistor. Don't really like those. The problem being that they're more prone to failure. They're not really designed as a heater, and so over time you can end up with a failure just in the resistor because it's being used as a heater when it's really not meant to be. So what we usually use instead of that is a 30 or 40 watt cartridge heater. Now the benefit of these is they heat up really quickly. They are designed as a heater, but the downside to that is if you don't have good control on it, you can end up throwing a hell of a lot of heat very quickly into the hot end. There's a certain control on the heating element that we have, which is a PID control. So one of the setup components is to actually calibrate the PID and make sure that that's working correctly. The actual nozzle itself, this is a genuine J-head Mark V. State of the art's probably moved on a little bit from this, but I've always had good results with the genuine article. There's a lot of Chinese sellers out there offering J-heads that kind of look the same when you look at them from outside, but there's really specific differences such as the way the heat break is assembled, how well these pieces remain joined, the size and shape of the actual melt chamber inside the head, which affects your performance as you're trying to extrude faster, plus generally consistency of result. Don't buy a cheap hot end. It's not worth the hassle. So in a fit of despair, I pulled this printer apart, put it into a box with the aim to come back once I'd printed all the replacement parts and put it back together again. So the first step here is just to go through. Here again is a bit of heat that's been applied. The heat that's come onto this means that it's distorted out of shape, and this particular piece holds one of the vertical rods, and of course if your two vertical rods aren't square to your printer, that's one of your critical problems that you're not going to be able to take out of it with software. So as we work through, pulling out a set of parts that are the new parts that we'll use to put this printer together, with the aim of making a singing and dancing phantasmagorical joy forever, a thing of beauty. When you buy a kit, your kit may not have all been printed on the same printer at the same time. One of the things that's quite important, these 4 blocks here form the support for the base of the printer. They get some threaded rods through, and if you set those up first time around on a flat base, and if they were printed on the same printer at the same time, you get some really good accurate start point leveling in your build. All of these little grooves here are designed such that the smooth rods will fit straight into them, and a slot here for cable tie to go over them, but that's a nice snug fit. I haven't had to do any machining on this because the printer that printed this set of parts, one of my other printers that I built, is really nicely tuned. One of the things you'll notice here in this set is the what's called infill, or support rather. Accidentally those were printed with support, and because I'm lazy, so bugger that, I'm not going to pull those apart. I'll just print another set. So I'm fairly confident that I ended up with a second set. Okay. Another thing that people often do with these kits is they'll use a spring coupler, which looks like the fanciest thing you can do for the project. The only downside is that they're actually springy in this Z vertical direction, and that's the axis that this driven shaft is trying to maintain consistency between your layers. So in trying to maintain a springiness here, it's giving you a rigidity around the rotation, but it's giving you a bounce in the Z axis. The option I prefer is to just use some cheap plastic tubing. Typically I'll throw a ball bearing in here off one of the 608 skate bearings, and then stick the Z rod on top. What that means is that the shaft can wobble if this is bent. It can travel around. The only point of contact is the thread between the lifting surface of the motor and the supporting surface of the X-axis. It's maintained, and it's got the flex it needs in the axis it needs flexing to compensate for a bent shaft. If your shaft is straight, you don't have a problem, but even the smallest of bends in that can cause a problem. A lot of the Chinese kit manufacturers, in their wisdom, decided that when Joseph Prusa removed the top constraint on the Z shaft, that it was making the printer somehow weaker. So they then went and put it back in. Unfortunately, that has the exact opposite effect of reinforcing the Z. If there's any bend in that shaft, we get an amplification of that issue, and it translates into wobble on the print. So rather than a nice smooth print like that, you end up with a banding that occurs. There's a lot of things like fender washers that people use. If you've got your belt set up on the right alignment, the belt will naturally travel to the center of the bearing. This is just a waste of space, effort and time.